Hey. Yeah, we'll take it.
Thank you. All right, guys. I'm Ricardo Martinez. This is Megan Ledoux, and that's Queen Win. We're here to talk to you today about our presentation. About our project, which is using neural networks to detect mines with sonar returns. Shorten it a little bit there for you. We're going to explain a little bit about what we've done so far, the challenges that we faced, which have been quite a few, and a little bit of the technical aspect of our project. First, I'm going to turn it over to Megan. She's going to give you a little bit of an abstract as to what the overall breadth of the project is.
So overall, we are set up to design a system. We're going to have input returns of the sonar coming back from the sonar. There'll be signals. From there, we're going to want to manipulate the signals to eventually determine what type of parameters the actual signal reveals, I guess. So we can determine the sediment type, bottom type of the ocean bottom, because the sonar is going to go through water. It's going to be the ocean bottom that we're actually determining. And then ultimately, we want to determine whether or not a mine actually exists at a particular location on which the sonars are signifying. So that is our main goal. Is we want to find out if a mine exists or not, and also what type of sediments the actual sonar is receiving.
There we go. Sorry about that.
So our accomplishments to date, it's what we've been working on for the past month or so, I guess. So we've done a lot of preliminary research. We've done research, a lot of readings, a lot of searches and stuff. We've kind of had to find information about practical sonars in the real world, and different things like that, the different components and the necessities, frequency, bandwidth, everything like that. We had to determine sediment types and actually how they are classified and their characteristics. There's many characteristics to a sediment type. It's not just, oh, it's dirt. It's also like there's grain size, there's reflectivity, density, that kind of thing, and we actually had to determine what characteristics there were, so we had to research that. And so far, we've also looked into filter design. We determined that we want a low-pass filter for the sonar signals to kind of make them cleaner, so we can actually work them out. We've determined a big picture. We know kind of what steps we want to take and in what order we want to take them. We need this preliminary research. We need to figure out parameters. We need to, ultimately design this neural network. We have to train the network, and then from there, take it as it goes. So we've determined the big picture and what steps we're going to do. As also, we've kind of just defined the signal features, which we'll go on later and talk about that. But the features ultimately will be what we train the network with. So that's what we've done. So Wee's going to take it over, and he's going to kind of explain the big picture of what we have so far, and we'll go from there.
All right. First of all, this is basically just a rough block diagram of what's going to happen. First, the return from the VSS is going to go all the way to a filter where it'll smooth out all the rigid, jagged areas that will be caused by the sand, and eventually it should normalize the signal. And then it'll compute all the features that we need from it. And for that we need, first of all, we need like a median filter to normalize all those features and smooth out all the that signal. You'll see the signal later on. And then afterwards, those features are going to go input it into the neural network, where we'll train it. It's basically just trial and error from there. And those neural networks will detect whether there's a mine at that specific position or not. Alright, and these are the sonar specifications. We're using the AQS 20 VSS. This is a volume search sonar, and we have a little picture of what it's going to look like. We haven't actually physically seen it yet. We've only been looking at the MATLAB files, you know, trying to compute all the signals. We actually got the signals from Dr. B, since she's worked with the VSS before. But basically, there's 54 beams in total, and they have 2 sets of horizontal beams. So if you can picture it, there's going to be one for the aft and one for the stern, where there's going to be 23 beams going across, scanning the ocean bottom, so that it'll scan, and once those beams are like centered onto the bottom, it'll give you a clearer signal. Once it goes outward, it'll give you a more distorted sort of signal. And it's gonna be operating around the 30 kilohertz frequency, so we can use that in our calculations later on. And these are what I explained earlier, where this is the center beam, which is 12. There's 23 in all, and outward towards this area, that's where it'll record a more distorted signal, and this will have a clearer signal right there. And here are the return signals. Oh yeah, sorry.
I'll take it from here. As we pointed out here, right here, these signals are going to be more distorted. Obviously, if you look at it geometrically, if you're looking at the ocean floor, this beam is going straight down, so you're going to get a much cleaner return on what it's passing over. The rest of these beams are fanning out in opposite directions. So what's happening is you're getting a much more distorted signal, which is right here on the left. This left signal actually represents beam number 1, which is on this side. This signal right here, which is of the same portion, same picture in time, is this beam right here, beam number 12, that's straight down. So that just gives you an idea of how, quote-unquote, dirty and noisy the signal looks. You have all these different ridges and peaks, and what we've actually managed to accomplish is we've taken this and we've used a median filter in MATLAB, and we've kind of smoothed this return out. From that return, what we are planning to do is, as Megan mentioned earlier, we're planning to take features from these returns. We want to take the amplitude, we want to take the width, we're taking the Fourier transform of it, we're looking at the bandwidth present at the peaks, we are looking at the slopes approaching those peaks. From these different features, we're going to take them and train our neural net. That's actually what we've been working on right now. We've been working on classifying and getting features from these signals. From these signals, as I said, we will also be able to determine the classification of the sea bottom. There are 7 different classifications. They're kind of redundant in my eyes because some of them, as you can see, there's sand, silt, mud, and we're actually working with mud, sand, and sandy mud. So it does get kind of ridiculous. Each one has its own specific conductivity, reflectivity, density, grain size, and all these will affect this picture that you're looking at right here. If you have something that's much more solid, for example, you'll get something that's pretty clean that looks like that. But if you have something with a lot of grains, has a lot of reflectivity, it's very grainy, you're going to get something like that. So these are the challenges that we're having to work around. As I said, right here, we're focusing on sand, sandy mud, and mud. This signal, as I mentioned earlier, will be smoothed, and then we'll pull all of our parameters off of it. We're using a median filter. We're also trying to design a Butterworth filter to see if we can get better results. We're trying to use the Butter filter command in MATLAB to see if we can get a smoother curve. So far, the median filter has given us the best results, however. From that, as I mentioned, these are the different signal features that we're looking for. This has been our biggest challenge so far. We've already smoothed it. The problem is we're not quite sure, and this is our unfamiliarity, with MATLAB on how to compute these functions. They sound easy, but when you have this written out as a function on a piece of paper, you can find all those things very easily. You just derive, integrate, so on and so forth. When you're looking at a picture, This is much more difficult to be able to tell a computer to extract these features from this picture. So it's one thing for someone to give you a sine, whatever, and you can pull out the frequencies from that, than having this. And that's our biggest challenge right now. We're trying to figure out how to tell MATLAB, hey, find these features out of this. So that's what we're looking for. Once we compute these features, we're, as I said, going to feed it to the neural network. We're going to train the neural network to recognize whether there's a mind present or no mind present. And then we want the neural network to also tell us if there is a mind or if there's not a mind, what material are we looking at? Are we looking at mud? Are we looking at sandy mud? Are we looking at just sand? These are the three things we've been limited to because the scope of the project is huge. It is kind of difficult. If you include all 7 of the grain types, then we would have to train it for 7 different grain types, as well as 7 different minds in these grain types. So we would have to extract features from several different things. Obviously, our final result is hopefully to train this neural network. That's what we plan to do. We're working on our pre-computation algorithm right now, and we hope to be done by the end of spring break. Any questions?
Can I say something? Can you
Sure.
go back to the last slide?
Sure.
I just want to mention one thing that I'm not sure if you really mentioned. We actually have the data for sonar within these grain types, sediment types that we did say, but these are without minds. So eventually, once we train this neural network,
Yeah.
it can tell us what grain it is, but it can't really tell us what mine it is. So what our another step that it seemed like we kind of missed or stepped over it was that we actually have to manipulate data to simulate a mine because we can't actually get that data. So that's a whole nother step in the process. And then from there, we would have to do the, computate the features, train the network again, and then
Thank you. I forgot about that.
do that.
That's another big challenge because we don't know what a mine looks like, and the Navy's not just going to hand over sonar reference to us. So we need to simulate one.
And
Of what
that,
we think one
that was
will
something that also when we were doing the preliminary research was a lot of things that I was sticking in Google, I was looking through files, it was just like, it would tell you a little bit, but it wouldn't actually like go in super detail. Someone had mentioned that maybe because it is some classified material or just harder to get your hands on.
Yep. Are there any questions, comments? Dr. B, I'm sure you've got a couple.
We'll discuss the comments in detail, but go back to your diagram. We are right now concentrating on the feature extraction,
Which diagram? This one?
the block diagram, the one with blocks. You will eventually have to use the raw return to get those particular features that if you filter out, you're going to lose. Okay, the most important characterization may be determined from a smooth, nice, easier to handle filtered waveform. However, there's some information that, as you said, the graininess, you're going to lose it once you filter it. So there's going to have to be a second path from the return straight to the computation, or maybe even straight to the neural network without filtering.
Right.
Okay.
Okay. Definitely add that to
List of things to do.
yeah, which is growing another minute. Any other questions, Dr. Demetrius?
A couple quick ones. So you just mentioned you don't have a clear knowledge about what would be the sonar return for mine. Now, how do you distinguish among those features that can be used to classify mine or not mine from?
It's a good question. It's actually something that we, as Megan mentioned, we haven't really been able to find much information on what a mine might look like, but we're going to infer from the different data classification types of bottom types.
Okay.
We're going to try to say, okay, well, if a mine was here, it would probably be this size and composed of this material, so it might give us a return that would look something like this, and then we're going to generate that return.
So you mean before doing the classification of mines, you want to first classify just the sediment of the?
Yes, we're
Yeah.
classifying just the sediment first.
Because a mine would eventually have a different material than
Right.
whatever that sediment would be.
We would hope that they wouldn't build the mines out of mud,
Okay.
because if they did, then we're in trouble.
Yeah.
I mean, as you can imagine, it could be, the return could be a mine in mud, so it would be a muddy mine.
And
So we kind of need to distinguish not only the sediment type, but also, what the mine material would be. And if it's covered, I mean, it only penetrates so deep.
And A big problem is,
So
Dr.
do
Chen.
you assume that the mine is like on the surface of the sea or
Somewhere-
somewhere?
It's gonna be buried.
It's gonna be
Buried
buried.
in the sediment?
Yes, it's gonna be buried in the sediment.
Okay.
But one problem, I actually spoke with a naval architecture professor about this. The harbors of the world are littered with garbage. So that's another challenge. We need to be able to hopefully train our neural network to recognize a mine instead of a hubcap. Things like that. People throw a whole bunch of stuff, and if the Navy's ever planning on driving over there, we need to make sure that that's a mine and not a hubcap, or vice versa. So that's something that we're looking into.
Just one quick question.
Sure,
Are
Doc.
you using any specific types of neural networks or?
We actually haven't gotten that far into the neural network
No, no,
research.
I'm just curious.
No,
Is there a
yes.
specific type that would be more
No,
appropriate?
it's a valid question. No, we actually haven't gotten that far into the neural networks right now. Our biggest challenge, as I said, is we're trying to just extract these features from the return itself. But we'll eventually get there, hopefully. Any questions, guys? Okay.
Okay, thank you, ma'am.
Dr. B, is it all right if I leave? Is it all right if I go? Seconds long, but then we have to pull it out of the water. We need to put in the new batteries, and then we need to put it back out there. Yeah, we'll be out there till at least 4 o'clock. We may be.
Okay, I don't know if I'm-
We're-